8th International Physics Olympiad year 1975 IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. Measure me if interested. My email is fred1996@hotmail.com, or you can use Skype name Eduard F1996. Problem number 2. The focal length f of a thick glass lens in air with a refractive index n, radius curvatures r1 and r2, and the vertices distance d, see the figure, is given by formula f equal this expression. Remark: Ri greater than 0 means that the central curvature point Mi is on the right side of the aerial vertices Si. Ri less than 0 means that the central curvature point Mi is on the left side of the aerial vertices Si, where I equal 1 or 2. For some specific applications, it is required that the focal length is independent from wavelength. Question A. For how many different wavelengths can the same focal length be achieved? Question B. Describe a relation between Ri, where I equal 1 or 2, d, and the refractive index n, for which the required wavelength independence can be fulfilled, and discuss this relation. Sketch possible shapes of lenses and mark the central curvature points M1 and M2. Question C. Prove that for a given plane convex lens, a specific focal length can be achieved by only one wavelength. Question D. State possible parameters of the thick lens for two further cases in which a central focal length can be released for one wavelength only. Take into account the physical and the geometrical circumstances. Solution for problem number 2. Question A. For how many different wavelengths can the same focal length be achieved? Solution. The refractive index n is a function of the wavelength lambda. According to the given formula for the focal length f, which for a given f yields to a quadratic equation, in n there are at most two different wavelengths, indices of refraction for the same focal length. So that was a solution for question A. Solution for question B. Describe a relation between Ri, I equal 1 or 2, d, and the refractive index n, for which the required wavelength independence can be fulfilled, and discuss this relation. Solution. If the focal length is the same for two different wavelengths, then we have equation f from n1 equal f from n2. Using the given equation for the focal length, it follows from equation we have this equation for both coefficients of refraction. Now we can reverse them and find that we have this relation. Now we can simplify it to this equation, and after subtraction we have this relation. If n1 not equal n2, which is obvious, we can get finally this relation. R1 minus R2 equal D multiplied by 1 minus 1 over N1 and 2. If the values of the radii R1, R2 and the thickness satisfy this condition, the focal length will be the same for two wavelengths indices of refraction. The parameters in this equation are subject to some physical restrictions. The indices of refraction are greater than 1, and the thickness of the lens is greater than 0. Therefore, equation 2 became d greater than R1 minus R2 and R1 greater than R2. So that was solution for question B. Question C. Prove that for a given plane convex lens, a specific focal length can be achieved by only one wavelength. If we take this formula for focal length and suppose that R2 is going to infinity, we can get limit f going to R1 over n minus 1, which is formula for regular thin lens. And this thin lens has only one root. That was solution for question C. Question D. State possible parameters of the thick lens for two further cases in which a certain focal length can be released for one wavelength only. Take into account the physical and the geometrical circumstances. Solution for question D. Again, we can use equation for focal length. It should have only one single root, and we can rewrite it in form of regular quadratic triplet. So that will be this equation. Here we can use regular substitutions for coefficients A, B and C. That will be this one, and from here we can write solution for two roots of this equation. That will be this one. But we have to use cases when we have only one root. That could happen in three different cases. So first case is when this triplet became duplet. It means that A equals 0 and this equation became linear equation. So we have A equals 0. It means that R1 minus R2 equals D. And in that case, coefficient of refraction n equals this expression, which must be greater than 1. So that was first case. Second case, it happened when coefficient b equals 0. It means that we have two roots. One is positive and the other is negative. And because negative doesn't make us physical sense, we have only one positive root. So that will be b equals 0, this expression equals 0, and because n squared equals negative c over a, which is equal to this expression, the root will be positive quadratic root from this expression, which must be greater than 1. So that was second solution. And the third solution is when this discriminant equals 0. So that will be b squared minus 4ac equals 0. And we have this expression. In that case, we have two roots, but they are equal to each other. And they are equal to negative b over 2a, which is this expression. And this expression also must be greater than 1. So we did all 4 questions for problem number 2.